Hello everybody and welcome to my confidence interval video, and in this video I would like to take a look at the process of inferential statistics referred to as estimation. And the idea between this video and the next one is we would like to lay the foundation of what is known as confidence intervals or interval estimation. We're going to lay the foundation, then I'm going to go into the gory details regarding proportions, and we'll take a look at some examples, and then we'll take a look at what's referred to as sample size computation. And this first part is going to deal primarily with the population proportion, and in the next video I will talk about the sample mean and how we use X bar to estimate mu. So in this case, this particular video is going to be divided up into three or four different regions. But this first part, this introductory, this part one, also will apply to the sample mean, estimating the population mean. So without further ado, let's go ahead and get started. All right. So suppose that you are researching for the Democratic Party and are interested in which candidate Democrats will choose to represent Colorado in the U.S. Senate that is currently held by Cory Gardner. So you survey 1,020 Democrats and find that if the election were to be held today, 46% would vote for John Hickenlooper and 43% would vote for Andrew Romanoff. So just focusing in on this 43% and this 46%, let's just note that this 46% is what we refer to as a point estimate. So going back to our summary statistics, all those summary statistics, if you want to use those statistics to estimate a population parameter, these are known as point estimates. So the idea in our case is to suppose that we start off with this population, and in this case the population would be defined as all the registered Democratic voters. It could be either in a particular city, a county, a state, or so forth. But the idea is that whatever the candidate or the candidates are in whatever region you're taking a look at, they all have access to this particular candidate or candidates. And if so, we can assume that there is going to be some true population proportion that is going to vote for a particular candidate. And we don't know what that population proportion is, but we would like to get a handle on this population proportion. So one of the things that we can do is go out and sample. And in this particular case, we could use, and nothing is stopping us from using something else, but for our sake, we can use p hat, which we have discussed quite a bit, as x over n, or the number of people that fit a particular profile, divided by the total sample size. So in particular, I'm taking a look at John Hickenlooper. So I could take a look at my sample and say who would they have voted for. And so all the people that voted for John Hickenlooper divided by the 1020. All right. So the question that we could ask, and I believe that is a fair question, and that is, well, will this p hat be exactly the same as this population proportion if I'm going to use p hat to estimate the population proportion? All right. So the answer to that question is probably not. All right. And the reason why it's probably not going to be exactly the same is this idea of sampling error. So sampling error results from using a sample to, notice, estimate information about a population. So in this particular case, we're using p hat as an estimator for p, and probably at the end of the day, we don't know what p is, but we don't think that p hat, or at least it's reasonable to conclude that p hat is not the same as p. Now, unless we were doing some kind of simulation or something like that, which we'll get into here in a little bit. All right, and the reason why as well is that the sample, we're only dealing with a sample of a population. Sample size, of course, does have a factor into this. But notice that a sample, no matter what, at the end of the day, will give incomplete information about a population. So we are losing some information. But the question is p hat doing okay, and is it doing a good job? So again, let's kind of come back and let's deal with John Hickenlooper here. So John is our guy, and remember earlier we said, well, 46%, if the election were held today, 46% said that they would vote for John Hickenlooper. But if I'm going to use that p hat of 46% to estimate the true population proportion, and knowing that there could be room for error because I'm working with a sample and not a population, that means I'm going to have some wiggle room going on here. All right, so if I was to ask, okay, that 46%, but knowing that there could be some error associated with that 46%, what kind of wiggle room would you give? And probably, if you sat there and ham-hawed about it, I don't know. So I came up with, say, well, what about a 3%? What about 3% margin of error, what we refer to as a margin of error? And we're going to get into this in detail later on. So here we're coming back and saying, well, I think that the whole population of Democrats would vote for John Hickenlooper, and I think that that true proportion then is going to lie somewhere between 43% and 49%. All right, so what we're actually saying when we slap on that margin of error is we think, or we believe, or we hope, or we have what is referred to as a confidence that somewhere between 43% and 49% the true population proportion is going to be in there. All right, now we're not going to know with absolute certainty if that population proportion will be in there unless we were able to ascertain information from all the registered Democrat voters. So this 3% that we put in there is this idea of a margin of error, which we're going to get into in great depth here in a little bit. Okay? So at the one other topic that we'll come back and revisit in a little bit is this idea of a point estimate, along with the margin of error, is going to give us what we call a confidence interval. All right, this confidence interval then is based upon this confidence level or level of confidence. And the idea, just loosely speaking, we'll put a tighter grip on this in a little bit, is that the confidence level is the amount of confidence we have that the interval contains the population parameter. And it's very important that you realize that the interval contains the population parameter, not that the parameter is in the interval, and we'll get into that in a little bit if you're sitting there and you caught what I said and scratching your head. Okay, so a confidence level is how confident we are that the interval contains the mean. All right, so we could go back in these last few minutes in our introduction that we talked about, and we can apply these exact same concepts to X bar, which I will discuss here in the next video. All right, so part 2, constructing and interpreting confidence intervals. Okay, so I just want to, again, reiterate this idea that this is estimation, and estimation allows for error. And so this error produces an interval, and this interval produces a confidence interval. And some people also refer to this as an interval estimate as well. So let's just recall that for the most part, not always, confidence intervals, especially with what we're going to be talking about with proportions and means, is always going to be in the form of some sort of a point estimate, in our case p hat, plus or minus some margin of error. So here p hat is our point estimate. So now we'd like to spend some time on what this margin of error is and how do we come up with it. So this part of the video moving forward, I'm just going to let you in on a little secret that there's going to be a lot of information, and you're going to have to do a lot of backpedaling. I'm going to tell you right now, section 7.2 I'm going to tell you that all of Chapter 8 is going to factor into this. And if you need, make sure that you go back and review the videos on that stuff. Make sure you understand about the normal distribution. So with that being said, I'm going to go ahead and move forward. And again, you feel free if you have to watch this video more than once. So one of the things we learned from sampling distributions is that p hat is distributed normal, and it is centered at p, and it has a standard deviation of root p1 minus p divided by n. All right, so before we get into the gory details, I want to now focus back in on what we mean by a confidence level. So we kind of said the confidence level earlier, and I kind of gave a little hand-waving thing, but this is more gory detail about a confidence level, or a level of confidence represents the expected proportions of intervals that contain the parameter if a large number of different samples is obtained. All right, so the idea, and I kind of mentioned this back in the sampling distribution, if you can go out, collect a sample, and then compute p hat or x bar, throw those people back in, resample, get p hat 2, x bar 2, and keep doing that, say, 100 times. All right, so if I could do this, and if I could resample 100 times, then I have these 100 estimates, which means that I can then form 100 confidence intervals. And if I take a look at those confidence intervals, then the question is, how many of those intervals will contain the population parameter? Now, I need to point out, you don't get to do 100 of these. You get one shot and one shot only. But let's take a look, see. So if we could repeat sampling, and in this case, the repeated sampling was 200 times, and the population proportion was known because it was a simulation. And as we can see, the population proportion here is 0.7. All right, so, and this left side here is 100 confidence intervals, and this other side here is another 100 confidence intervals. Now, if you go and you take a look, this was done at a 95% confidence. So if I construct 200 of these intervals, note that 95% of 200 is 190. So that means that according to my confidence level, according to this definition, then that means that 190 of those confidence intervals should contain the true population proportion, which means that 10 of them won't. So if you come over here and you take a look at these 200 intervals, note that these red ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of these red intervals do not contain the population proportion. All right, so notice that 190 of them do. So that means that 95% of my confidence intervals contain the population parameter. One thing you can observe is that these population intervals are all over the place. Now remember, these intervals are centered at p hat. So p hat is the thing that changes. Notice that p is 0.7 and remains fixed. So notice we said that the interval contains the mean. All right. The reason is because the intervals are bopping around and the p remains fixed. I think I said mean, but I meant proportion. Okay. So the proportion is fixed. It doesn't move. So the interval contains the mean. Now remember, in practice, you get one shot. So the idea is that out of all these green lines, you don't get 200, you get one. So the question is, do you get the green one or do you get the red one? And the answer to this question, you don't know. You don't know with absolute certainty. That's why you have a confidence and you say, well, I don't know, but I'm 95% confident that it does. But with absolute certainty, we don't know. So let's take a look now, and we are ready and we are now prepared to move forward into this idea of margin of error. All right, so here I have a normal distributions because p hat is distributed normal, And so p hat is something that I can go out and I can collect based upon the data. Okay, so we know that p hat from prior discussion is normally distributed and is centered at p. So here's my normal distribution, and here it is centered at p. All right, so this red area is if I could go out and collect all p hats, all of the p hats, then this interval, and I'm going to, for sake of discussion, for argument's sake, just use a 95% confidence level. I could have picked any one that I wanted, but I chose 95%. So that means that if I go out and I could choose a sample size little n based off a population big N, then our big N choose n different samples that I could collect, and that's a lot of different samples. And if I could collect every one of them, 95% of those proportions would fall in this region. So notice if I knew P, then I could come all the way out here to this fence line, if you will, and over here to the left of this fence line, if you will, and that will contain 95% of all of my p hats that I could compute, and they would fall in that red region. Okay, so the question now is how far out can I go? And when I ask the question, how far out can I go, one of the measures that we talked about back in chapter 3 when we talked about sampling was z-scores. And remember, z-scores is the number of standard deviations away from the mean. The z-score is the number of standard deviations away from the mean. So in this case, p is the mean. So we want to know how far out from the mean that we have to go. All right. So let's take a peek at what this means. So under a standard normal distribution, we want to find out how far away we need to go. So based upon your prior work, and this is some reference that you can go back and take a look at, in 7.2 subsection 2, you found out about x's, finding x values for a given upper-tailed area, for a given lower-tailed area, and for a given middle area. So that part back in chapter 7 is coming back to haunt us. So let's just observe that we want to compute this. So under the standard normal distribution, remember a mean of 0 and a standard deviation of 1, if I want to be 95% confident, and remember confident is now this area underneath the standard normal curve, then how far to the left and to the right can I go? So to determine how far, then I just put this into StatCrunch, put my mean, standard deviation, put this in, and then we click compute, and notice it'll tell us we have to go 1.96 standard deviations of p hat to the left and to the right. So now I can replace those fence lines with the fact that we go 1.96 standard deviations to the left and to the right, or another way of writing it is p plus 1.96 sigma sub p hat and p minus. So now we can rewrite the graph in this interval form right here. But notice that this is written in terms of p, but p is something I don't know. So one of the things I could do is I could go ahead and do some algebraic manipulation, okay, and I can actually come up with this. So it would be a good exercise for you just to practice your inequalities and then subtract p, then p hat, and then do some math magic to come up with this inequality. So notice now my unknown inequality is in the middle, and now it's in terms of some things that I know or I could compute. So this, written compactly, would be saying, in order for me to be 95% confident, then I have to go 1.96 standard deviations of p hat that was discussed about back in our sampling distribution days. All right. So this is kind of how we kind of put a specific and how we come up with the 95%. So now what I'd like to do is to generalize and come up with any confidence level. So if you want to be 90, 95, 99, 82, 88, 97, you pick the confidence level. All right, so to generalize this, we have our 1.96 for the 95% confidence. All right, so let's just recall that here now it's not going, the red middle area is not going to represent the 95% proportions, but now it's going to be whatever level you decide to choose. So another piece of notation that you also learned about back in section 7.2, subsection 2, is this alpha area. So this alpha area, in case you didn't, I don't know, to make a better understanding of this alpha area, is that alpha area always refers to either upper-tailed area, lower-tailed area, or two-tailed area. So in this case, since we're working with a middle confidence level, then the alpha area is going to be this left-tailed white area and this right-tailed white area here. And by symmetry properties of the normal distribution, the amount of area here is going to be equal to the amount of area over here. And because a normal distribution has an area of 1, if I know the confidence level, then I can compute the alpha area over here by taking 1 minus the confidence level. So working with a 95% confidence level, then 1 minus 0.95 is 0.05, which says that there is 0.05 area in both the upper and the lower tails. And by symmetry properties of the normal distribution, that means that there must be alpha over 2 in just this area here, and alpha over 2 in just this area over here. And going back to our 95%, that means that in both the areas we just said is 0.05, divide 0.05 by 2, and you get 0.025. So this area is 0.025. So again, if you put in the 0.025, plug that all in, this is where we came up with the 1.96 for the 95% confidence. So now notice in general that this fence line area right here, we now denote it as Z alpha over 2. Some people call this a Z-score. Some people call this the Z critical value. So this fence line right here, for whatever confidence level, is the critical value. So plugging this back in and substituting for all of this right here on the left-hand side over here, all right, this guy right here, then this becomes P hat, okay, plus or minus Z alpha over 2 sigma sub P hat, which I make that substitution, and we get this right here. So this, ladies and gentlemen, becomes almost our confidence interval formula, okay? But the problem here is we have P right here, and I'll get to that in just a minute. Now, some statisticians, and a lot of times you're going to see this, but there are some common or popular confidence levels. And if you're working with proportions and you have these common confidence levels and you have to manually construct these, then one of the things that you can do is just go ahead, and if you have a 90, 95, or 99%, then you can use these values over here. So notice in our previous discussion, I chose 95%, and no matter what, if you're working with proportions, then 1.96 is always going to be that Z critical value. All right, so if you want to commit these to memory, which I don't, because you're going to be using StatCrunch, which is in a totally another video, to compute your confidence intervals. There's really no need for you to memorize those. All right, so this is the derivation that we have right here. And the question is, well, I don't know P. That's what I'm trying to estimate. So notice that right here, basically what we do is we substitute our P hat in for those P's that we don't know. And this is a popular thing to do. And so this will give us our confidence interval. So our confidence interval then is going to be P hat plus or minus the Z alpha over 2 times the square root of P hat 1 minus P hat over N. And again, you should check these conditions, which are not unfamiliar to you as of yet. All right, so that concludes my discussion regarding the margin of error and how we come up with these confidence interval formulas. This is probably the most conceptual, mathy part so far that we've had to deal with, and it probably might help if you understood a little bit, but anyways, feel free to go back and review the video. I have a hand-operated way of computing these just so you can kind of see how to do it, but then again, when it comes to homework, quizzes, and your project, I do recommend using StatCrunch. All right, suppose you are researching for the Democratic Party and are interested in which candidate Democrats will choose to represent Colorado in the U.S. Senate that is currently held by Cory Gardner. You survey 1,020 Democrats and find that if the election was held today, 46% will vote for John Hickenlooper. So now what we'd like to do is to compute and interpret a 92% confidence interval for the true proportion of registered voters that will vote for John Hickenlooper. All right, so this should look a little familiar. So the first thing you would have to do if you were to manually do this is to compute alpha. So alpha is 1 minus the confidence level. So we end up with a value of 0.08. Then our next step is to get this tail area, the value of one tail area. So we just take 0.08 divided by 2 and we end up with 0.04. Our next step now is to compute the Z critical value. All right, so you can either compute the upper tailed area or the lower tailed area. And normally when I have taught manually to do this, I have always chosen the lower bound area. So I will stick with that. So on StatCrunch, you can go to your normal calculator and notice that you can put in 0 for the mean and 1 for the standard deviation. And notice that this left bound area here is the exact same for this 0.04. So I plug that in, and since it's a lower bound area, I have to make sure that I have this less than in here. And notice that it comes back and it tells me negative 1.75. So the critical value then is 1.75. Now you may be asking, well, where's the negative? When we report back critical values, we just report these back as positive numbers. All right, so you will never, it is not common to put the negative if you compute the lower critical value. Now, if you were to compute the upper critical value, then it comes back positive. And secondly, and finally, notice that this 1.75, right down here in our formula right here, this sign is absorbed right in this plus and minus anyway, so you don't really have to worry about it. So now you just take this whole thing and come up with a fancy schmancy way of plugging this into your calculator. But when you do, you should end up with 0.4327 and 0.4873. Okay. And again, I would recommend using StatCrunch to compute these, because if you mess up just a little bit, you're going to be having headaches. So the idea now is, what does this mean? What does this interval mean? All right, so we come back and we just got to remember that a confidence interval is the level of confidence we have that the interval contains the mean. And our level of confidence in this case was 92, a confidence level of 92. So we are 92% confident that the true proportion of registered Democrats that will vote for John Hickenlooper to be the Democratic candidate for the U.S. Senate is between 0.4327 and 0.4873. Remember this sentence because this is the appropriate way to interpret confidence intervals. Now notice in StatCrunch, the other video will show you how to do this, and notice that we come up here, shows us something about fairly close, fairly similar. Okay, so that is my handheld example so that you can kind of see this all in its down and glory. But again, I don't recommend you to do this, and I know some of you will, but don't, because it's going to become a computational nightmare. So the next part coming up is on sample size for proportions. All right, the next part is sample size computation. So we got to take a look at something that is very interesting here. If you take a look at the level of confidence, and then if you come over here and take a look at the critical values over here, notice that as the level of confidence increases, notice that the critical value increases. And if you go back to that margin of error, that z alpha over 2 square root of p hat 1 minus p hat over n, notice that that means that as everything stays fixed, as your level of confidence increases, notice that z-score increases. And so by default, that means that the higher the level of confidence that you have, that the wider the interval becomes. So this anomaly is something that we have to be very concerned about, because remember, the idea is that we are using this to estimate the population proportion. So the question that you have to answer is that if you want a high level of confidence that your interval contains the mean, then that also means that you are allowing for a large amount of error. And remember, a large amount of error does not give us a lot of accuracy if we want to use p hat as our estimator of p. Notice if you have a lower level of confidence, say an 80%, then the interval becomes smaller, which means you have less wiggle room. So the question is, for your estimator, do you want a lot of wiggle room, or do you want a small amount of wiggle room, knowing that p hat is going to be an estimator? And I'm hoping that you see that you want to have a small amount of wiggle room. So now the question becomes, how can I have a higher amount of confidence, okay, but have a smaller amount of wiggle room? All right. So let's take a look. A sociologist wishes to conduct a poll to estimate the percentage of Americans who favor affirmative action programs for women and minorities for admission to college universities. Suppose that she wants to have an estimate within 4 percentage points, but wants to also have a 90% confidence. So again, notice here is that we have to say, all right, what is going to be my allowable amount of error? What is my margin of error? What am I going to allow? So at what level of confidence? All right. So basically what this question is asking us is that whenever we want to come up with this p hat, but we want this part right here to be 4 percentage points. And so at the end of the day, when I compute my p hat, all right, then the question is, how do I fix this so that my percentage points, okay, is only 4% margin of error? Okay. Now, when we go on and we do this, notice that once I click my sample, p hat's pretty much fixed. So there's not much that I can do here. So the question is, what can I do with this guy right here? So taking a look at this equation, you come up with the amount of what we call error. So now this error becomes here. And notice, once you fix your level of confidence, then Z alpha over 2 becomes fixed. So if you say, I want to be 95% confident, then you already know that Z alpha over 2 is going to be 1.96 from prior discussion. If you want a 90% confidence level, then you know that from that table, Z alpha over 2 becomes 1.645. If you want to be 88% confident, then all you have to do is go out and do the first 3 steps of the confidence level interval and then come up with that Z alpha over 2, and then that becomes fixed. So P hat is already fixed. So the only thing that we have wiggle room is with this N. All right. So now this just becomes an algebra question, and it comes up with solving for N. Now, this is not algebra class, so I'm not going to bore you with the algebra, but here's what the bottom line comes down to. Is that when we solve for N, the question we have to ask is, do we have a prior estimate for P hat? If you do have a prior estimate for P hat, then you're going to use this N equals P hat, 1 minus P hat, Z alpha over 2 over E squared. If you don't, then you're going to use this 0.25 Z alpha over 2 divided by E. Now, for those of you that are wondering where did the 0.25 come from, the author gives a nice little discussion. And it involves some quadratics and an upside down parabola. And where does that upside down parabola become maximized? Okay. So let's take a peek-see at how do we use these. So notice this exercise says that a sociologist wishes to conduct a poll to estimate the percentage of Americans who favor affirmative action programs for women and minorities for admissions to the college or universities. What sample size should be obtained if she wishes the estimate to be within 4 percentage points with a 90% confidence if she uses a 2003 estimate of 55% obtained from a Gallup Youth Survey? So in this case, we have some prior information on P hat based on a study that was done, in our case, 17 years ago. So using that, knowing that information means that I'm going to use this one. Okay? So let's just observe that we need first that Z alpha over 2. So as I said a few minutes ago, we have to we do the first 3 steps. So Z, we compute alpha, and then we compute alpha over 2, gives us 0.05. So now we compute Z alpha over 2. And again, if we use StatCrunch to compute this, we get the mean of 0, 1. You put in your 0.025, and notice you get this negative 1.6448, da-da-da-da-da. Or notice here at 90%, you could have just automatically used this without doing these 3 computations right here. You could have skipped that altogether and went straight to this one right here. All right. But if you don't have one of those 3, then you have to do those previous 3 steps. And I just kind of wanted to point that out. Again, watch the StatCrunch video because you don't have to do all of this. So plugging into the formula 0.55, plugging all this information, I get this decimal answered. I did round to about 3 decimal places. And if you notice in the gray box, the author tells us always round up. We do not go out and survey 418.588 people, okay? We don't do that. Round up. We always we're statisticians. We love data. So round up. I don't care if this said 4.18.0001. You round up. to the next whole integer. So notice, same question. I'm just going to jump to this last sentence. What sample size should be obtained if she wishes the estimate to be within 4 percentage points with a 90% confident? And we could have stopped right there, but notice it says if she does not have a prior estimate. Since we don't have a prior estimate, means we're going to use this one. So plugging in the information that we have, notice it says we come up with 423. So the idea is that if we go out and sample 423 people, okay, then the proportion, this should give us a proportion of 4%, and we should have p hat plus or minus 0.04, and we can compute that, and we should be 90% confident that within that interval the true population proportion is contained. All right, so that concludes our discussion regarding confidence intervals and our introduction to estimation. I promise the next video should not be this long. Thank you.